Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. So in this video, we're going to continue to cover Module 2. In particular, we're going to cover the Section 2.5, the resources, and Section 2.6, threads. In the previous sections, we have covered the PCB, the process control blocks. This is actually a data structure that used to record the status of the processes. Okay, now we're going to actually talk about the resources, what kind of resources we're going to have in the computer systems and how the operating system manages these resources. Now let's talk about Section 2.5 resources. The operating system maintains numerous resources that the process can request and release at the runtime. Remember, each computer system has resources, right? And then operating system actually manages these resources. So in the previous section, we talked about two lists. One is called ready list. Basically, it's called stand for ready list. Now, for all the processes that are ready to run, then these processes are going to be placed on the ready list, based on the priority, right? And then we have a whole bunch of waiting list. Okay, actually, for each resource, there's a waiting list. Okay, now let's talk about this in much detail. Okay, so remember that the hardware resources include keyboards. Okay, so keyboards is hardware, pointing devices, printers, diskers, tape devices, camera, speakers, and many other type of devices. The hardware resources also include memory and also the graphics card and also the CPU, if you wish. It can be also regarded as the hardware resources. Okay. So there are also many software resources, like the input-output buffers. Okay, or many of the buffers on the device controller, and logs on database tables, messages, timers, and many others. These are also called software resources that a program may need to use. Okay, now how does an operating system manage these resources? Okay, now remember, for process, the operating system uses the process control block, right, to manage the resource. Now, for each resource, like a keyboard or printers, the operating system also use a data structure, very similar to the data structure for PCB. Now, operating system use a data structure called resource control block, RCB. Okay, it's called RCB. So RCB is a data structure that represents a resource. Okay, so now depending on the type of resources, the specific implementation and the contents of the RCB vary between different operating systems. Also, depends on the type of resource. But the following is the generic structure that can handle many type of resources. Let's see the next slide. But before we do this, let's say for each resource, like I say, resource 1, I have RCB 1. Okay, resource 2, I have RCB 2. Resource 3, I have RCB 3. And then these resources has some generic structure. Now, the structure for the resource RCB are much simpler than the PCB. Remember, PCB have many different fields, but the resource is actually only dedicated to a specific task. So their structure is much simpler. So now each resource requires, a generic resource may requires 3 fields. Now that's depend on operating system. It may actually contain more fields. Now the first one is the resource description. Okay. Resource description basically contains the description of the properties and the capabilities. Okay, you have to tell the users that what this resource is supposed to do. Okay, and also the resource state. That's the other field. The resource state shows the current availability of the resource. Okay, so whether the resource is available. Now, due to the nature of the different resources, some of the resource may have only one instance. That means there's only one single device, and if that resource is used by one process, then the other process cannot use it. And now some other resources may have many instances. So even though it's one device, but however there are many different instances. For example, a resource like a controller, they may have a couple of buffers. Buffer 1, buffer 2, buffer 2, buffer 3. So each buffer can support one process. So one process can actually use that, grab one buffer to use the resources. And then the next process request for the resource, then you're gonna find out, oh, there's another buffer 2, so available. So the other process can also utilize the resource. Okay, so then the state basically says whether a resource is available. If it's a one instance resource, then if no process is using it, then it's available. Now for the resources with multiple instances, that depends on the number of instances. If you have 2 instances, then it will basically allows 2 processes to use it simultaneously. So that means if the resources has 2 instances and one instance is used by a process, then it's still available because you have the resource has 2 instances, and it's still allow another process to use it. Okay, and then there's a waiting list. That's the other field. The waiting list basically, so when a process requests for a resource and the resource is currently unavailable, then the process, it's a PCB basically, so the process is going to be put on the wait list. Now, in order to do this, now remember, so a process could be wait for the ready list. It's in the ready list. That means the process is waiting for a CPU. Okay. Now that's only when a process gets all the resources it needs. Okay. So if the process gets all the resources it needs, then the process is going to be in the ready list. Now, when a process requests for resources and the resource is not available, so that means the process is not ready, right? So now initially the process is in the ready list, and then if a process requests for additional resources, and that resource, for example, a process requests for RCB, the resource 1, and the process, then that RCB 1 is not available, but the process is request for the resource 1. So in that case, the operating system is going to remove this process from the RL, the ready list, and then place the process into the waiting list of the RCB1, because now the process requests for RCB1 and RCB1 is not available, so the process now is not ready anymore. So it's going to be removed from the RL. So this process is going to be, going to be put on the waiting list of the RCB1. Okay, so now the RCB1 may contain some other processes, right? So all the processes that are waiting for the resource 1 will be placed on the waiting list of the RCB1. Okay, these are all the processes waiting for the RCB, the resource 1. Now, if a process is on the list of the waiting list of RCB1, that means this process cannot be in the ready list. Remember that? So only the process that gets all the resources, then it will be on the ready list, the RL. Okay. Now, same thing for the resource 2. Okay. So there's a resource description, state, whether it's available or not, wait list. Same thing for resource 3. Now, it's possible that a process may request for more than one resource. So a process may, let's say a process P1 is probably request for resource 1. And it's also possible for the P1 to request for process 2. Okay. Now, it's possible process 1 request for resource 3, but resource 3 is available. So then the resource 3 going to be added on to the other resources in the PCB of process 1. Okay, so the resource, it's not going to be on the waiting list of resource 3, but it will be put on the other resources in the PCB of process 1, the PCB 1. Okay, it's a little bit complicated, but it's not really that, difficult to understand. Okay, so here's the summary of the a generic RCB of resource R. As you can see that the RCB contains 3 resource field. One is resource description and the state and the waiting list. Now that's just a generic RCB for a particular resources or a resource for particular operating system. You may see some more fields, but these are some kind of common fields for any resources. Okay, so that's something we just discussed. Like a state, this basically shows the current availability of the R. So there are 2 scenarios. If the resource has 1 instance versus the resource has multiple instances. Okay, the waiting list is basically only contains the processes that are currently waiting to acquire the resources, but the resource is not available. Okay. Okay, now let's discuss a little bit more about the relationship between the processes and the resources. Okay, how the operating systems deal with the processes and these resources. Now take a look at the diagram on the right. Now this is a PCB, right? Okay, so you can see all the fields for the PCB. Now let's say that's the PCB for process P. Okay, that's the PCB for process P. And then one of the things we need to pay attention to in the PCB is the other resources. when you deal with the resources, when a process deals with resources, that's the field we need to pay attention to. Okay, so this is actually a linked list which points to the resources that this particular process is allocated. Okay, so that's one of the RCB here, and it just points to the RCB. So that means these are the resources that are allocated to this particular process P. Okay, so that's a PCB for a process P. Now, operating system used RCB to manage the resource, right? We just mentioned that before. And the structure for the data structure for RCB is much simpler than the PCB. Okay, remember the RCB contains, a typical RCB contains the resource description, right? That's the top one. And the state, which basically shows whether the resource is available, is free, or currently used by another, allocated to another process. And then a waiting list. Okay, let's say that's the RCB resource control structure, control block for a resource R. Okay, now you may have some other resource. Let's say resource Q, and there's a RCB for resource Q, and that's the RCB for resource R. Okay, and if you have a more resources, then you're going to have a more RCB for the resources. Okay. Okay. Now, when a currently running process, let's say P is currently running, okay, currently running process needs a resource. Let's say P needs a resource R, The operating system executes a request function. Okay, that function, the request resource function, then allocate the resource R to the process P. So it tried to allocate the resource R to the process P. Okay. Now, the operating system first is going to check the state of the resource. If the state say, oh, this resource R is available, so then operating system is going to actually say, well, I'm going to allocate the resource R to the process P. So I'm going to add the, the RCB R, which related to the resource R, on the linked list, okay, for the other resources. And then the operating system continue to run the process, because the process is running and request for resource R, and then the operating system check the resource R is available, and then allocates the resource R to the process P, and add then add the RCB, to the other resources on the PCB of P. And the process continue to run, because the process gets what it needs. Okay, everybody is happy. Now, let's talk about another scenario. So let's say process P requests for resource R, and resource R is not available. So in that case, things are going to be different. Okay, now let's start over again. Let's say, okay, process P request for resource R, okay, and then the operating system check the state of the resource R and find out, oh, the resources are not available. Sorry, it's not available. Okay, so now what we do? Let me actually erase that one. Okay, erase that one. because at this moment, because the resource R is not available. The resource R is not available. Okay. So now what? Operating system will block process P. Okay. What does that mean? So when process P is running and all process P is ready, so basically process P is currently on the ready list. Now, if you forget the ready list, just go back to the previous slides. And the ready list is a list that contains all the processes that are ready for the CPU. Okay, so technically you can say ready list is the process that are ready to run, ready for the CPU. Okay, now ready list is organized into different priority, right? Here's the lowest priority processes waiting for the CPU, and a little bit higher priority processes waiting here. So suppose that P is over here somewhere. Okay, P is okay. So that's the process P is actually on the way to, and currently running, right? Now, if P is actually request for the resource R, and then the operating system check the resource R and check the state and find out it's not available. Resource R is currently allocated to another process. Then what the operating system gonna do? The operating system gonna first block the process. Okay, what does block mean? Block means you're gonna change the running. It's no longer running. Okay, and also it will remove the process from the ready list because it's not ready. It's waiting for resources to run, but the resource R is not available. So it's not ready anymore. So you're going to remove the process P, remove the PCB from the ready list, and place over here. And put on the waiting list of the RCB R. Okay. Okay. So now the process P is on the waiting list of the RCB for the resource R, and it's removed from the ready list. And then the operating system is going to trigger the function called reschedule. Okay, because now it's up to the operating system to choose the next process to run. It basically you're going to pick the next process on the ready list. Okay, the next highest priority processes, in the ready list, and then the operating system is going to actually pick this process to run. So this is actually the how the operating system deal with the processes and resources. Okay, let's take a look at another scenario. We know that a process can request for a resource, and then it will actually modify the related list and modify the PCBs and modify the RCBs. So we actually discussed this in the previous slide. Now, what about when a process tries to release a resource? Okay, when a currently running process P, okay, let's say that's the PCB for P, for process P. Okay, wish to release a resource R. So let's say currently the resource R is here. For resource R, it's there. Okay, so then when the process P done its job and it doesn't need the resource R, so it doesn't make any sense for the process P to continue to hold the process R because the resource R, right? Because the resource R may be needed by other processes. So the operating system executes the release function. The release resource function allocates the resource R to the next process on the R's waiting list. Okay. So let's say here's the resource R, and we have RCB for resource R. Okay, here's the RCB. Remember that's the resource description. And the second field is a resource state and a waiting list, right? Okay. I call it RCBR, right? So now, if P wish to release the resource R, then if R's waiting list contains no process, okay, now the waiting list is empty. Okay, now currently the state is not free, right? Because currently the resource R is allocated to the process P, right? So it's still on the list of other resources on the PCB of P for P. So it's not free, okay? But there's no other process waiting for the resource R. So then if P decide to release a resource R, and then the state of R is changed to free, right? The state is changed to free. And the P continue to execute. In that case, the resource R, RCB or R will be removed from the list. And then this becomes free, okay? As there's no process on the waiting list, okay? Now, things are slightly different if, let's say, let me actually delete this and talk about the other scenario. So if there's another process Q, okay, and now there are probably many other processes, not just one process. A list of processes actually on the waiting list, and the process Q, so then is at the head of the list allocated R. Okay, so Q is on the waiting list, and it's on the head of the waiting list. Okay, so so currently it's still the RCB R is on the list of the other resources for PCB P, right? Now, if P decide to release it, so the RCB R will be removed from this list, and then the operating system is going to check the RCBs of the R and find out, oh, the next one should be Q, right? Okay, so then what happens is, so the PCBQ is currently actually on the waiting list of resource R. So you're going to remove this, okay, from the waiting list. And then, remember, we have to update the PCB for process Q. Now, I'm not pay attention to the other one, but I'm going to focus on the other resources. So There might be other resources actually allocated to the process Q, but in this case, because Q is on at the head of the waiting list for resource R, so then Q will actually the one to get the right, and then Q will be removed from here and put the RCBR on the list of the other resources for PCB Q. Okay, and then what else I need to do? So then we're going to put the process Q to the ready list, right? So the ready list is like, so you need to put the process Q. Now, depending on the priority, you're going to put a process Q to the ready list because the PCB queue has been removed from the RCBR, the waiting list of RCBR, and then this will be removed and put in here. Okay. Now we have a situation that okay, PCB is done. So PCB of P release the resource R, and the PCB process P will continue to execute, and then so the queue gonna grab the resource, and then the resource is going to be put in the other resource in the PCB of process Q, and then process Q also going to be added to the ready list. So now the process Q is fighting for the CPU now with the other processes. Okay, it could be like the situation is that the PCB Q has a higher priority than the process P. Even though process P is currently running, the PCB Q now it's ready. So the PCB Q has a higher priority than PCB P. Then PCB Q gonna get the next CPU time and kick the PCB out. So that's basically what happens when a process actually releases a resource. Now, one of the important functions in the operating system is the scheduler function. Now, the scheduler function determines which process should run next and starts the process. Now, how the scheduler function will be triggered? Okay. Now, the scheduler function will be called frequently at the end of each of the process and the resource management functions. Now, these are the process and resource management functions: create, destroy, request, release. Okay, if operating system call the create function and create a new process. Okay, if operating system create a new function, new process, and then operating system need to call the scheduler function and decide and review the newly created process and the existing process, and to determine which process is going to be run next. If the newly created process has a higher priority than the existing running function and running process, then the current process is going to be kicked out of the CPU, and then the operating system is going to allocate the newly created process, and the new process is going to be running. Okay. Now, when a process is destroyed, then you have one fewer processes running. So then the scheduler function will be kicked in, and then again the scheduler function need to decide for the remaining processes which one I need to pick to run. Okay, the destroyed function may be the function the destroyed actual process may be the processes that's currently running, right? So who knows? So once the process is destroyed, the situation has been changed. So the scheduler function need to reevaluate all the processes and decide who's going to be running next. Now, the two other scenarios is the request and the release. We just discussed these two cases. Remember, the request function will be called when a process is running and a request for a resource, say process P request for resource R, okay? And then if the resource R is available, the resource R will be allocated to the process and the process continue to execute. Now that's the easy case. Now what about if the running process request for resource R and the resource R is not available? Remember, then this process will be block itself. And the operating system is going to remove the process from the ready list, right? From the ready list, and this process, the PCB of this process will be put on the waiting list for the resource R. Okay, the RCB of the waiting list of the RCB of resource R. So now this process is actually on the waiting list for the resource R, and removed from the ready list is not running. So in that case, the scheduler function will be kicked in and decide who's going to be next process to run, because the current process blocks itself. Okay, so now the other case is also clear, right? When the current running process decide to release a resource R, okay, and then the operating system gonna actually check whether there's any processes waiting for the resource R. Let's say process Q is on the waiting list for resource R, and then once the process P released the resource R, the Q gonna be able to allocate the resource R, and then Q probably gonna be ready, and the process Q gonna be placed on the ready list. So now in this case, the scheduler gonna be kicked in and decide whether the process P will continue to run or the process Q going to be able to run, because if the process Q has a higher priority than process P, and then the operating system going to kick the process P out of the CPU and then let the process Q to run. So there's a various different scenarios. Okay, so the scheduler function will be kicked in every time when things like this happens. Okay, let's talk about our last section in Module 2, Section 2.6, threads. Okay, remember that every time when user try to execute a program, by clicking the icons or type the command in the command line interface, and then a process is created. Now every time when a process is created, then a process control block will be created. A process control block is a data structure, right? Just used to represent the current state of a process. It's a structure, big structure. Okay, so wherever the execution blocks, so if the process is running and then it blocks, then all the process is waiting for some resource to become available. Normally the process will block itself. Okay, so it doesn't matter what happens. Maybe only just the process block, simply because the process is waiting for its one of the resources, and then maybe some other part of the process can continue to run, because only one portion of the process requires the resource. However, with the current implementation, if a process blocks itself, the whole thing is blocked. It doesn't matter which part of the process, which things you are doing. Okay. So that's a kind of problem. Okay. So the other thing is the process is kind of big. So when you try to create a process, and then the operating system is going to create a big, data structure called a PCB. Okay, now if a computer gonna actually trigger a process, create a process, and this process gonna run for a very short period of time. So then the operating system is going to create the PCBs and update the PCBs, and suddenly after just a very short period of time, and the process complete its job, and then the operating system need to destroy the PCB and need to actually eliminate everything related to the PCB. And then operating systems are going to call the create function again and create the PCB for the same application. Okay, and then you have to go through this process again. Okay, that's a lot of work, a lot of waste. And that's typically what happens. For example, if you are running a computer browser you want to surf the browser. So the same application will be triggered, the same program will be triggered again and again. The same program will be triggered and then run and then eliminate. And then the same program is going to be triggered and the process is running and then finish. So the same program will be triggered again and running again. So continuously. So in that case, it's kind of costly for the operating system. So now people try to figure out a way to resolve that kind of situation. Okay, and then thread is actually created. So a thread is an instance of executing portion of the program within the process without incurring the overhead of creating and managing separate PCBs. Okay, so you want to run the piece of code, okay, execute the, trigger the program and start a process, and you want to start another process but associated with the same program, and start another process associated with the same program. So the same program is going to be started again and again as a different processes. That's process. Now there's an easy way to deal with that kind of scenario. Then people use thread. Okay, now using thread are going to actually somehow increase the performance and save the resource. Let's talk about this a little bit more later. Okay, let's say if you want to start a browser, so you click the icon for the browser like Firefox or and the other browsers, right? So then you start a PCB for the browser. So the PCB contains a lot of things. It also contains the code, the files that this browser use, and a whole bunch of fields. Okay. Now, if you want to run another browser window, then you can actually click the icons again, and then you're going to create another. Okay, another PCB. Now, these two PCB are basically running the same program. Okay, they're running the same code. Now, it's just each of the so they're basically running the same code, but they're different processes. They're different processes. So it has a different thread of control. Okay. Now, but they share the same, mostly share the same common things. Maybe the resources and the code, and they actually, so a lot of area of the fields, between PCB1 and PCB2 are the same. There's no difference. But however, you need to create a dedicated PCB for each of the process, but these are all different browser windows. You can create 10, 20 browser windows, right? So that's a lot of waste. Now, modern operating system actually use the concept of thread. So that means you gonna create a browser window. For the browser window, you're gonna create a process. Okay, and then you have a process control block, right? And then if I want to continue to create another browser window, I'm not going to create another PCB. I'm not going to create another process. What I do is, because there are a lot of things that are shared, a lot of fields are shared. So the only difference is probably for each browser, I'm going to, view the different website. I'm going to run different things, run different apps. Okay. So, but the rest of things are pretty much the same. So they may have a different thread of control when you actually, so it's the same code, but each actual browser window, maybe for this browser window, it's running the instructions, like instructions number 100. So it's running somewhere, running the instruction 100. But the other browser, I'm running the instruction 20. So probably they have a different thread of control. Okay. So in that case, I can create one process. And then for each browser window, I'm going to create a different thread. I call it thread 1, thread 2, thread 3. I can continue to do that. Okay, there's only one process, but you have a multiple threads. However, all these threads are basically share the same program, share the same code, share the same open files. Maybe they are actually doing, there's a big common area. There are big overlap. But each thread has its own thread of control, because they are viewing different things. They are doing independent job. Okay, so one thread actually of the browser window is actually you are watching the movie. The other one is you are doing some of the editing work, and some other things you are just view a website. So they're probably running different app, but they are actually associated with the same application, the same program. So because the thread has its own thread of control, so each thread requires a dedicated structure to keep track this particular thread, and this is called a thread control block, TCB. And this one also has a TCB. This one has a TCB 3, thread 3. So in that case, instead of you have three actually browser windows. Instead of creating 3 different processes running different, with different 3 different PCBs, and you're gonna create one process with 3 threads. So then you have one PCB and 3 thread control blocks. Now, what's the benefit of this? And you will see that each TCB, these TCB basically share the same program, share the same common part. So TCB is very small compared with a PCB, which is actually pretty big. And then these PCB has a lot of actually overlaps. They basically store the same information. Most of the part they store the same information. Only small portion, like they're different. Okay, so that's called that's the thread. Okay, so what's good about thread? So thread is actually, if you actually running a thread, so then if a thread is blocked, it will only block this particular thread. It's not going to block the whole PCB, whole actually process. It's only one process, one thread is blocked, and the other thread can continue to run. So that's one thing. Okay, so even though there's a one PCB, which can actually save a lot of actually memory space, and also it's going to increase the performance. We will find out later, because when you do the context switching, which means that when you do in a multi-programming environment, when you actually switch from one process to the other, so you need to save the whole process control block and load a whole process controller into the computer CPU. But now, when you switch between threads, if you say currently thread 1 is running, okay, and then when you switch from thread 1 to thread 2, only thing you need to do is you need to switch the thread control blocks. You need to save the current thread control block and load the next thread control block. And most of the process you don't have to change. Okay, the PCB part you don't have to change. You only change the thread control block part. So the context switching going to be very quick, because you only actually save a small data structure and load a small data structure. So from this perspective, thread actually works like a process, because it has its own control, path of control. Different threads don't make it run. Different thread basically they run by their own. The only thing is that because different threads are actually running the same application, running the same code. So technically, thread is like a process. Each thread is like a process, but it's not the whole process. So that's the reason why many times people call thread a light-weighted process. Okay. So let's talk about the implementation of threads. A thread can be a user thread or a kernel thread. Threads can be implemented completely within user application. Now, in that case, a thread library provides functions to create, destroy, schedule, and coordinate thread. So let's say I have, here's a kernel space, here's a user space. Now, if a user thread is created, it's created by a thread library. It's in the user space. So the library maintains the TCBs within the user process. So let's say if a process is created, it's created by the operating system. So let's say a process P1 is created. So then the operating system is gonna create a PCB1, right? Corresponding to P1. And then if process P2 is created, another PCB will be created. Okay, so the PCB contains the a whole bunch of different area, like CPU states, process states, and the other resources, memory. So there's a whole bunch of fields. Okay, and all the fields for the PCB. Now that's PCB1 and that's PCB2. Okay. So now, if for PCB1, for the process P1, if the application wants to create a multi-threads, okay, want to create a user level threads for process 1. So then these threads are going to be created through the library, right? Thread library. So you're going to create, for example, we want to create two threads for process 1. So let's say I'm going to create a thread T1. Okay, and then thread T2. And then the corresponding thread control block will be created. TCB2, TCB1, PCB2. Okay. Now, so the process P1 has two threads, T1, T2. Now the PCB for the process 1, PCB1 is in the kernel space. So it's basically the operating system is aware of this. But the operating system is not aware of the TCB1 and the TCB2. Operating system is not aware of the T1 and the T2, the two threads. Okay. Now what does that mean? So when the user want to support the time sharing, for example, like a multi-threading using the time sharing. So that means somehow you want to support the time sharing between these two threads. So you want to use the CPU to support, to execute T plus thread 1, and then switch to thread 2, and then switch back to thread 1. Okay, if you want to do this, which is very similar to the context switch between two processes. So you can switch back and forth between two processes, P1 and P2. But now you want to support the context switching between two threads. So how does the system do that? Remember, the operating system is not aware of this. So this job should not be done by the operating system. So it could be done at the application level. So it could be controlled by the library, because the library controls the scheduling, the thread scheduling. So if you want to actually allocate a CPT for the TCB1 or for the thread 1, or allocate the CPU for the thread 2, then it's the job of the library. Okay. So now once a process is created, like a process 1 is created, then the process is associated with the code and the data related to the process. Now, for a single-threaded process, so that means there's only one thread for the process, then there's only one stack. But in this case, the process 1 has two threads. Now, each thread is going to have its own thread of control, which means each thread contains its own CPU state. Now, CPU basically state contains all the data stored in the CPU. For example, like process a program counter, which is the memory address of the next instruction to be executed. So then when thread 1 is executing, the thread 1 gonna actually basically store the TCB1 gonna store the program counter for that thread. Okay. And also thread 2 has its own program counter, PC. Now also, because each threads are running at its own path of control, so then the stacks going to be different. So you're going to have stack 1, stack 2. So stack 1 is corresponding to thread 1, stack 2 corresponding to thread 2. Now, how the operating system organize all this. So now we have two things. One, if the computer system, the operating system supports multi-programming. So that means I can use the time sharing to, run the process 1 and the process 2 and then switch, using the context switching. Now, in process 1, P1, I have two threads. So the two threads can actually do the context switching. But that context switching is controlled by the library, right? So by the library, not by the operating system itself. How does that work? Now let's take a look at this. Now here's a timeline. And here we have process 1. And here we have process 2. Okay. Now, so let's say we start from here. Now, if the operating system, if the computer system support multi-programming, so the operating system is going to allocate using the scheduler, going to allocate the process 1. So it actually allocate the CPU to process 1. So CPU going to run the process 1. And then after time, certain period of time passed, the operating system say, oh, it's time to switch to process 2. So then I'm going to run process 2, right? So that's process 1, process 2. And then I'm going to switch back to process 1, process 2. Okay. Now, in particular, using the multi-programming, in particular using time sharing, so the time interval are going to be the same. Okay. So after the same period of time, you're going to switch to one process, and then after run a same period of time, it switch to another process. It switch back between process 1 and process 2. So which is good. So you can run two processes. Now, how does the context switching between two threads actually fit into the diagram? Okay, let me actually use a different color. So, because the context switching between two threads are completely within the process P1. It's controlled by the library, which is also in the user space. So let's say in the library implementation, the scheduler decides that I'm going to actually switch back and forth between T1 and the T2. So I'm going to run some period of time for P1, and the thread 1 going to run a certain period of time, and then switch to thread 2. Now remember, when you do the context switching between two threads, T1 and T2, it's completely within process 1. So that means only the process 1 is taking the CPU, and then the library for these threads can actually, implement these switching, context switching. So let's say when I run in the process 1, during the time the process 1 is taking the CPU, and then library going to kick in and load the thread 1 during that time period. And then after a certain period of time, and then I'm going to load the thread 2. So I'm going to switch back and forth. Now that's the context switching between two threads, and that's the context switching between two processes. These happens at a different level. This is at the lower level, and that's at the application level. Okay, and then while the process 1 is still taking the CPU, then I'm going to switch back to T1, But soon, the operating system say it's time to switch P2. So then process 2 start to execute. And then once, context switch again, once there's a context switch again, and a switch back to P1, and then the library going to continue to work to finish its undo job, unfinished job. For example, in the previous time block, and T1 only executed for a small period of time, so you're going to continue T1, okay, and then switch to T2, T1, and then T1 and T2. So you continue to do this. So you need to realize that the context switching between thread 1 and thread 2 are completely in the user space within the process. It's actually controlled by the thread library. Okay. So the operating system is not aware of all these what's happening inside process 1. So that's the okay. Let's take a look at the kernel level. Thread. Kernel level threads. So again, let's take a look at the example. Okay, suppose I have a process. Okay, I'm going to use process A. Okay. So then there's a PCB A. Okay. Again, that's the kernel level. And that's the user. Now, so once the process A is created, then the operating system is going to create the PCB A corresponding to process A. Okay. Now, if the thread is supported at the kernel level, if process A say, okay, I'm going to run 2 threads. So then you're going to create 2 TCB, TCB1, TCB2. Which basically stores the CPU state. Now, when you look at the diagram, it's very similar. Okay, it is very similar. Okay, so again, you have a code, you have a data, you have a stack 1, stack 2, which basically store the temporary information for the thread 1 and the thread 2, and then you have a library, right? Now, I take it back, not the library here, because it's installed in the kernel level. So the library is also in the kernel. So the thread control block 1 and thread control block is also in the kernel level. Okay, so these both associated with the same PCB. Now that's the major differences, because the thread actually control block is implemented in the kernel level. The CPU is aware of the multi-threading for the process A. Okay, now that's the difference. Now suppose I have a process B created, and there's a PCB B, right? And then this is it. Now process B could be multi-threading as well, but let's say process B has only 1 thread of control, just 1. Okay. So in that case, now if, let me actually draw the same diagram. Let me actually free up some space. let's see. Let me actually delete that one. Okay. Now what happens in this case is, suppose I have a process B and also PCB B. Okay, let me actually put a small one here, PCB. That's a PCB. So let's suppose I have a process A and a process B. Now in that case, when the multi-programming, if the operating system support the multi-programming, and the operating system is aware of the multiple thread for process A. So in that case, when you do the CPU allocation, then the operating system gonna say, okay, process A has 2 threads, right? So then I'm gonna allocate process A thread 1, okay, and then I switch to process A thread 2, and then process B, and then process A thread B. So because each thread is going to be counted as a data, CPU going to allocate the dedicated, time for each thread, because thread is actually in the kernel space. That's the major differences, because CPU is aware of this, which is kind of good, right? So the creation and the destroying of the thread is also done by the library, thread library, but this library is actually in the kernel space. Okay, now let's actually discuss the user level and the kernel level threads more. So let's talk about the advantages of user level threads. We call the ULTs. Over the kernel level threads, we call the KLTs. Okay, now because ULTs do not require any cooperation from the kernel, so ULTs are much faster to manage, and thus many more can be created than the KLTs. So that's a good advantage, big advantage, because you can create as many threads as you want, because it's basically implemented at the user level. Okay, because of every time when you try to create something, request for anything to the kernel level, you need to make a system call. It's a very costly process. And the second one is application using user level threads are portable between different operating systems without modifications, because kernel is actually somehow related to the type of the underneath hardware, the CPU, but the user level it's just a high level. Okay, so to make things better is that the user level user level threads can be actually run even on the system that does not support multi-programming, because it's completely in the user level. It doesn't change anything in the kernel. Okay, that's a good thing. Okay, now nothing comes for free. And now, then what's the main disadvantage of a user level threads? So the user level threads are not visible to the kernel, which is good, but it's also a bad thing. Because why? Because if a user level thread blocks, so let's say you have a process. This process has a 3, 4, 5 threads running, and suddenly this particular thread blocks. Okay, so if this blocks, the operating system going to think, wow, process P wants to block itself. So then operating system is going to block the process P. It doesn't really matter. It's only just one thread because operating system doesn't even realize this process P is multi-threading. Okay. So if one thread blocks, then the whole process blocks. Okay. That's a bad thing. So, and also ULTs, the user level threads cannot take advantage of multiple CPU. Now, if you have a multi-core system, now that's really a bad thing, you know. If you have a multi-core system, you have two CPUs, then you cannot split a process. Say, oh, I have two threads in this process, so can I run thread 1 in CPU 1, run thread 2 in CPU 2? And so I need to split the process. No, you cannot. Okay. So you cannot take advantage of multi-CPU because the process is perceived by the kernel as a single thread of execution. Okay. It's just once the process is defined, and then it's predefined, and how the process, the instruction going to be executed is basically it's already determined at the compiler time. So you cannot split it. Okay. That's the bad thing. So many modern operating systems take a combined approach. So the kernel supports a small number of kernel level threads, and each application can implement any number of user level threads, but some of the user level threads can be mapped to the kernel level threads. Okay, so this is actually a combined approach, which in some ways solve the problems of the user level threads. Okay, let's illustrate how the operating system combines the user level and the kernel level threads. Okay, suppose this is the hardware. The system has two CPUs. Okay. Now, remember that if we only use the user level threads, then operating system cannot take advantage of these multiple processes, multiple CPUs, because if the multi-thread is only running at the user level, so operating system only support if you only support multi-programming. If the operating system support multi-programming, allow the process to run concurrently, then you can actually take advantage of this, but you cannot take advantage of the multi-threading. So in many cases, the operating system many operating systems support the combined version. So they actually support a limited number of kernel level threads. Now you may ask why don't support an unlimited number of threads? Because as I said, the kernel level threads are very costly, because every time when operating system create the kernel level threads, you're going to make a system call to create. It's almost the same kind of hassle like creating a process. So that's not good. So that's why operating system support some kind of a predefined number of threads. Let's say kernel level thread K1, K2, K3. Because these three threads are, operating system aware of these three threads. So they can actually use the time sharing, so allow the three threads to share these two CPUs, right? Take advantage of these two CPUs. Now, at the user level, let's say a process 1. Okay, a process is created. And this process has a 4 user level threads. I call it U1, U2, U3, U4. It running back and forth. Okay. Now, if the operating system does not support kernel level threads, then the thread process can actually directly deal with the CPU. But now we can actually do the mapping. So let's say I have four threads for process 1, right? And process 2 could be also contains a couple of threads. So what I do is I can actually map the user level thread 1 to kernel level thread 1. Or I can map user thread to kernel level thread 2. But as I say, that you have a more user level threads than kernel level thread. So you need to figure out, okay, I think thread 1 is very important in here. So I just use a dedicated kernel level thread to map it. And for the rest of these three threads, I share one kernel level thread. Okay, so when you switch back and forth, you can actually assign K1 to CPU 1, assign K2 to CPU 2. So you allow the CPU 1 to run processor 1 user level thread 1, and you use the CPU 2 to execute the remaining threads in process 1. Now, that's good. At least I can split some of the threads to a different the processors to different CPUs, right? But still, since U2, U3, U4 I share one kernel level thread, if U2 blocks, you're gonna block the whole portion of this. Okay, so that's still the problem. But at least you're gonna solve some of the problem. That's the trade-off we may face. Okay, so you can dynamically allocate some of the user threads to map the kernel thread, so you can take advantage of the multi-threading at the kernel level to a certain extent. Okay, that's the trade-off. Okay, so I think that's pretty much all for this chapter. Thank you.